Welcome to Brain Vision.
Here we're going to be finding the total magnetic field due to two sources, one of which is a wire, so we'll need Ampere's law, which you may use to find that the magnetic field due to a wire and its magnitude is a product of the fundamental constant permeability of free space, mu naught, times the current in the wire over 2 pi times the distance from the wire. The direction of that is a circle going around the direction of the wire, figured out by using your right hand, and we'll do that in a little bit. But we need some points to find the total magnetic field, and we will have to use superposition. That is, the magnetic field total is a sum vector of the uniform B naught that points to the x plus the magnetic field of the wire. And the direction of that magnetic field of the wire will depend on what position you're looking at. So there are several positions that have been identified. One is 1 meter away from the wire, which we put right down the y-axis going through the xz plane at the origin. The other one is 1 meter out along the x direction. And finally, there is a point C in the negative z direction, 0.25 meters behind what we're looking at in the negative z direction. Okay, so we have two magnitudes to figure out for the B wire, but let's figure out the direction. So the right-hand rule, usually what I do is I put my thumb in the direction of the current of my right hand, and then I see which way my fingers curl around the wire. And so what I see is in the front on the z-axis, the wire is going back to the negative x. On the other side, it's going to the positive x. And it comes out in the z direction in the front and goes into the minus z back behind. So that's going to be important when we think about those 3 points in the magnetic field of the wire. So let's get to it. For point A, okay, we're going to figure out the magnitude of the B wire is mu naught, which is 4 pi times 10 to the minus 7, a constant, times the current, which, let's see, they give that as 8 amps. I think I wrote that down. Let's do that, 8 amps. Okay, so it's a substantial current. So we'll put in 8, and I'm going to be calculating in SI units, so I'll be a little bit sloppy with my units. And the distance is 1 meter. So using SI units should give me Teslas when I'm all done. And that works out to be 1.6 times 10 to the minus 6 Tesla. And to be careful at point A, the magnetic field is direction is minus x. So let's work out the total magnetic field. We're going to add to it the B0, which is to the positive x, and then the Ampere wire equation, which is to the minus x. And so that comes out to be a really tiny amount. Minus 0.1 times 10 to the minus 6 Tesla in the x-hat direction. Yeah, magnetic fields tend to be quite small. From wires, anyway. Okay, point B is at a distance of 1 meter on the x-axis. And let's just check the direction on that. That is in the positive z direction. For the wire magnetic field, the magnitude is the same as before because we're still a meter away. But the direction now is positive z. And so our total magnetic field now will have two components. One in the positive x and one in the positive z. Okay, and one more point. Point C is at a distance of 0.25 meters. So we'll want to recalculate the magnitude. And I see that the magnitude will be 4 times higher than it was with a meter separation. That's easy enough to figure out. And the direction again, well, let's see what the direction was. To the positive z. Oops, no, we're on the wrong side. Back behind there, the direction is actually, I show it as a little dashed arrow. It is pointing to the positive x on the negative z side. So that will add to the B0. And make the total quite a strong, much stronger field. And yep, that's how you work out the magnetic field at different points due to two sources. And it wasn't too bad because one of those sources was uniform.